Hello students, in this video we will finish chapter 2 by talking about some simple machines, the ramp, the lever, and the pulley. And various versions of these machines show up in various disguises, you could say, in practical applications. So first of all, the ramp, and of course we've already seen this with inclined plane problems, but we've seen it from a slightly different perspective. In this case, we're not just saying, okay, there's this ramp here or this inclined plane here, and you have to analyze what the different forces on a mass on that plane are. It's saying we're going to deliberately use an inclined plane, a ramp, to reduce the force that we have to apply in a specific way. So the idea of these machines is to reduce the necessary force to accomplish a task. Now, when you are reducing the force, I forgot to put a right angle on there. When you're reducing a force, you have to do it at the expense of something else. And in this context, it's at the expense of some sort of a distance that's involved. So this comes at an expense of increased distance, and this could be in two forms in the examples that we have here. So this is either over which the force must be applied, or in the lever arm. And that depends on whether we're talking about a ramp or a pulley or a lever. In the case of levers, the distance that you're increasing is the length of the lever arm. You need a longer lever. And in the now you'll also get the force that you're applying to the lever. You're going to have to apply that force over a longer distance because you have to move this end of the lever arm a longer distance in order to get this end to move a certain amount. But there's longer distances involved in all cases. And so an analogy would be, if I ask you the question, is it easier to move to lift up 1,000 one-pound weights one at a time and go and walk them over to a table and then come back and take the next one and the next one and the next one 1,000 times? Is it easier to do that? Or is it easier for you to pick up a single 1,000-pound weight and walk over to the table and set that down? Well, there's no way that you can lift the 1,000-pound weight. It's too heavy, so you couldn't do that at all. Whereas the other way would take you some time, but it would be doable. Now, this whole idea is, this idea of reducing the necessary force, this is called mechanical advantage. And the ratio by which you can reduce the necessary force is the size of the mechanical advantage. And so this comes at an expense of increasing the distance. In the analogy I gave you, you'd have to walk back and forth carrying weights 1,000 times instead of just doing it once. But the weights you were having to carry would just be 1,000th of the weight of the whole entire weight. And so it would make it doable. Now, when you put these two things together, you see it's a trade-off. So when I say this comes at the expense, so it's what machines are is it's giving you a trade-off. And a way you could think about this, or an expression that you could associate with this, is that there's no free lunch. You can't you can't get something for nothing. Yeah, you can reduce the force involved, but it comes at the expense of increasing the distance. So let's talk about these machines individually now and see how they work. So the way the ramp works is the force that you're applying decreases from mg to mg sine theta, and the distance increases from h to h divided by sine theta. Now this is in the following particular situation, and this is actually the same problem that was in that very first problem in chapter 1, where they were illustrating the 5-step solution method that they want to give you. And so the idea is that you have a platform and you have a mass that you want to lift up onto the platform. And this platform has height h. And if you lift it directly, the force that's required is mg, because that's the force that's necessary to cancel out the force due to gravity. The downward force on this is mg due to gravity, and so you need to be able to overcome that force by exerting the same force upward in order to lift it. So if instead you push it up a ramp where the angle here is theta, well, then from our inclined plane problems, we remember that the component of force going down the ramp here is mg sine theta. So you no longer have to overcome the force mg in order to lift it. You just have to overcome the force mg sine theta, which is a smaller force because theta is going to be between 0 and 1. So this is the force now that you're having to overcome. So that's why the force is decreasing from mg to mg sine theta. Like I said here, decreases from mg to mg sine theta. Now the expense is that here you just had to lift this a distance of h, whereas here you have to push it all the way along up this plane from the beginning here to the end. So the increased distance is going from this distance here to this distance here. That's the change in distance that you're having to apply that force in order to get it to go up the ramp.